Welcome back. This is part 3 of our video series on VASA. In this video, we'll go through the examples on direct daylight and visibility. You'll learn how to compute your own metrics using voxel-based analyses. But first, let's see how to control the axes and extents of voxel models. Okay, so here I've got Dynamo and we've got VASA installed. We'll go File, Open. Here are all the examples that come with VASA. You'll remember that we covered the first 4 of these examples in the previous 2 videos. In this video, we'll be covering the next 5 examples. So we're going to start with example 5, rotated axes. Now this example demonstrates how to rotate the voxels with respect to the main coordinate system. So if we read the comments there, it will suggest that we adjust this voxel rotation slider and see what happens. So let me just move the model a little bit, and then we'll adjust that slider. So I'm gonna actually set it to 0 to start with, and then we'll drag it. And you can see when the rotation is at 0, the voxels are all aligned with the walls of the building. So they look quite flat, but as we increase the rotation 5 degrees, 10 degrees, etc., we're starting to see a serrated pattern because the voxels now are at an angle relative to the building geometry. And we'll keep increasing the angle 30 degrees. Let's go up to 45 degrees. At 45 degrees, we should be seeing, if we zoom in, a perfect sawtooth pattern. And in fact, let's go and crop off the top of the model so we can see into the building. All right. So now we have a bit of a better view of the walls. And we'll continue to increase that rotation angle. We're at 45 degrees, we'll go to 50, etc. And the angle of voxels changes. And when we get to 90 degrees, the voxels are now again aligned with the walls, so the walls look flat. Let's actually zoom out a bit, and we'll put the top back on the building, and we'll do that again, but we're going to focus now on the extents of the model. So you can see that that sort of the outline of a box around the model that shows how big the entire voxel model is, and you see it just encompasses the geometry. So now we'll start at 90 degrees, and we're going to go backwards now. So as we go back, as the angle changes, you'll see that the extents will grow so that they still encompass all the geometry in the model. And so they get larger until we get to around 45 degrees, and they'll start shrinking again. And then as we approach 0 degrees, they'll be as small as they can go, just going around the geometry. And of course we can go negative, and then they'll expand again, and they'll contract as we go down to 0, so they just fit the geometry. Okay, I'm going to actually set that to what it was originally, 15 degrees. And now that we've seen the extents, I'm actually going to hide the extent. So let's go and turn off the preview on these display extents nodes. Now let's zoom in and take a closer look at these axes, which are what allows us to change the rotation angle. So if we, so I should mention, but before we get into how to do this, I should mention, like, why would you want to rotate the axes? Like, you might be thinking, well, don't we want the voxels to be aligned with the walls? So shouldn't we always have a rotation of 0, which is the default? Well, I mean, it is more efficient to have voxels aligned with the walls, but Well, for one thing, the geometry of the building may not be aligned with the main coordinate system. So you may need to rotate the voxels in order to ensure the voxels are aligned with the walls. But even regardless of that, you may just want to experiment with different rotation angles. So you have the option of doing that using these axes objects. Okay, so here we have, here's where we're creating the axes object. So if we go to VASA and click core, we'll notice that there's three objects: axes, extents, and voxel model. And in the first examples, we skipped axes and extents because the defaults worked for us, and we just went straight and create a voxel model. But if we want more control over the voxelization process, we actually want to use these other objects. So if we want to rotate, we need an axes object. And you'll see there's two ways to create an axes. Here we're using axes by unit lengths and voxel origin. And let's go through these parameters. So the first two take length objects. The first one, seen unit length, is the units of the geometry, of the scene. So the geometry here happens to be in feet. And so we've just, all we're doing here is making that explicit. And we're using this length object, length in feet, which is producing this this object that actually is aware of units. So it actually knows it's 1 foot. And if you want to see where to get that node, it's in VASA under utils, lengths, and then you can see in feet, also in centimeters and inches and meters. So that's how we're saying the scene unit length. Now the voxel unit length is the length of the coarsest possible voxels. So here we're giving it 1 meter, same as the coarse voxel width, but in this case, since we're using these length objects, it actually knows it's 1 meter. And because it's 1, actually defaults to 1, so we don't actually need that code block there. I could just disconnect that and it'll still give me 1 meter. But suppose we wanted to have our voxels to be 4 feet at maximum. So then we can select an in feet node, we can delete that one. And then we can change the code block to 4. So connecting that up produces 4 feet. Then we can set that as the width of the coarsest voxels. But I'm going to undo that and go back to what it was before with 1 meter. Okay, so those are the length units. Next is voxel origin, which lets us offset the origin of the voxel model with respect to the main coordinate system. But here we're not doing that. We're just using the default, which is 0, 0, 0. Next, we have the voxel rotations. That's what we use that slider for. So here we got 15 degrees. So now the axes are being rotated 15 degrees. We can see that here. Look at that red line going across, which is the main coordinate system. Look at the black line, which is the axes being used for the voxel model. That's a 15-degree separation. And last, we have the vertical level of detail, which we're saying to 2. So what that means is that the voxel, we're always going to use a level of detail of 2. Remember, that means we divide the height in half twice. So we divide 1 meter in half twice, so 25 centimeters. We're using 25 centimeters for all our voxels, regardless of what level detail we use in the horizontal direction. Okay, so that's how we create an axes object. And just to show you what, how you view them, you don't have to view the axes objects, but here we are. We're using these 2 nodes that you can find under core axes, and one of them is display axes. I'm going to actually turn them both off and turn them on one at a time. So first we have display axes. We'll preview that. So that just gives us these 3 lines that just shows us the directions of the of X, Y, and Z, but specifically for the voxel models. And then we also, if we want, we can also show the origin voxels. So preview that. And now we see the possible voxels that we can use with the set of axes. So the coarsest ones are 1 meter by 1 meter. And then the next coarsest voxels are 50 centimeters, 25 centimeters, and then, it's at 12 and a half, 6.25, and the narrowest one is 3.125 centimeters. Again, always 25 centimeters in the vertical direction, because that's fixed with the axes. Okay, so the axes come with a bunch of nodes that may be useful. I'm just going to show you a couple: the voxel height and the voxel widths. So this, if you don't want to calculate the voxel dimensions yourself, we can connect those nodes up. So the voxel height is 25 centimeters, but we're in feet, so it's 0.82 feet. The voxel widths, these are all the possible voxel widths that you see there. So it starts at 1 meter, but that, again, we're in feet, so 3.28 feet, 1.64 feet, etc. Okay, let me just delete those nodes. So we create the axes. How do we create the voxel model? Well, here we're using voxel model by triangles and axes. So if we go into our menu, open up voxel model. Remember in the previous examples, we'd used either by geometry or by triangles, but now you can also use voxel model by geometry and axes, or what we're using here, by triangles and axes. So if you create your own set of axes instead of using custom axes, if you create your own, you generally want to use the same axes for all the voxel models. So then you'd just be using those nodes there that include the axes as an input. And then once you do that, the rest is the same as normal voxel model. So again, we got the finest level of detail, which was saying to 4, and you can carry on using all the analyses after you've created that. Okay, so that's how to create axes and how to rotate voxels. Let's move on to the next example. Won't save. Next, we have reduced extents. So this model is showing us how to voxelize only a portion of the geometry. Because remember, by default, VASA will try to create a set of extents that encompasses all the geometry you supply to it. But maybe you don't want to voxelize everything. For example, maybe we only want to voxelize this house, and we don't want to voxelize the terrain around the house. So in that case, we want to restrict the extents before we do the voxelization. And the comments there will suggest that we change these offsets of the extents. So let's do that and see what happens. So let's start with the lower Y offset. We can move that down, and we can see that offset changing, or back up. Oops. If we move it too far up, it doesn't. There's nothing to voxelize, but that's how we adjust that. Let's try the upper Z offset. So we can move the top of it up, we can move it down. Let's try the lower X offset. Move that down, move the lower Z offset down. Yeah, so you get the idea. I'm just going to undo those changes. You can change the extents of the model. Okay, so how do we do that? Well, in this case, we have to create both an axes and an extents object. So first, we're creating axes, and just to show you, the other way of doing that. Remember, there was two ways to create a set of axes. So here we're using the other node by coarse voxel width and origin. So here we here we're using that coarse voxel width parameter that we've seen before, and we're just giving it the value 4 for 4 feet. Again, we're not explicitly saying that we're using feet this time, but because this with this node you don't actually specify the units, but you have to know what the units are. So 4 feet for coarse voxel width. In this case, we're changing the origin. So previously we just used 0, 0, 0. Now we're using a specified point, and if we want to see where that point is, we'll have to display the axes. So right-click, display axes, and we'll see that this new set of axes has an origin kind of right in the middle of the house. So that's the origin. The rotation is currently just 0, and again we've got the vertical level of detail. We're using the normal value of 2. So now we've got our axes, and now we create an extents object. So there's 2 ways to create an extents object. One way, and there's no example of this, so I'm just going to click and show you what this node looks like. One way is to specify the indices of the corners of the extents. And every voxel has a unique set of indices. So if you want, you can experiment with that to learn how voxels are indexed. The other option is this by axes and 6 offsets node, which is what we're using there. And I think that might be a little bit more intuitive. So each offset is a number of voxels from the origin. So the lower offset, that's being set right now to -108. That's -109. So there's 109 voxels between the origin there and kind of the left side of the building, and then 107 voxels from the origin to the right-hand side there. So we set all of the offsets, and that creates a set of extents. And then we have extents, then, as you can imagine, if we go into voxel model, you want to use these voxel model creation nodes that have extents. So either by geometry extents, or what we're using there by triangles and extents. Yeah. So now we know what all the different ways to create voxel models. There's just one more node which is just by extents but no geometry. So with this node, you would give it the extents. You don't give it any geometry, and it gives you an empty voxel model of the right size with no filled voxels inside. All right. So now we know how to create extents and restrict. Restrict the size of the voxel models. This may seem like a very easy thing to do. I find that it's not that easy in practice. It's very easy. I mean, the concept is easy, but it's very easy to make a mistake. So just to give you some examples of what might happen, you may set the extents perfectly, like we've done there, but then at some later point, the rotation might get changed. And so suddenly the extents no longer make sense anymore. You're missing parts of the building. And if you're not showing the extents, and if you're not showing the voxels, you may not notice that happened. So that's one example, something to watch out for. Another one is it's very easy to forget to set this voxel level of detail parameter on the extents. So we'll just disconnect that. And now what just happened? Well, the level of detail had been 4, which is the normal default. But now it's changed. When I disconnected, it's changed to 0. So 0 means that the voxels are actually 2 to the 4 times bigger. They're 16 times bigger in both X and Y, which means I've actually got 256 times as many voxels. And so what might happen now, if I didn't notice, is suddenly my operations may slow down considerably, because I've got a voxel model that's 200 times bigger than I thought it was going to be. So that's another potential issue. Now remember, normally those voxel level details get set automatically to the finest level detail available in the voxel model. But remember, here we're setting this before we've created the voxel model. So there is no finest level of detail in the voxel model because it doesn't exist yet. So that's why this voxel level detail parameter defaults to 0. And so that's why we need to be extra careful with that one. So let's connect that back. Another thing to be aware of with extents is that certain operations may not give you the results you expect if the extents are too small, for example. So let's just we go into the VASA menu. Let's go into operations, surface operations. Let's try expand along Z. So this one grows the voxels that are filled. It grows them in the Z direction, and the offsets default to 1. Let's set the lower offset to 0, and let's use a slider, an integer slider for the upper offset. Let's give it the bounds 0 and 10 and connect that, and so I'll set to 0 for now. And now we'll connect the voxel model to expand along Z and view that. And if we zoom in, now if we adjust the slider, it's going to expand in the vertical direction. So I'm just going to change it to 1 first. You can see the roof goes up by 1 voxel, the floor goes up by 1, 2. Now we'll keep increasing it, but watch what happens. Instead of the roof maintaining its shape, it ends up saturating at the top, because this expand along Z node, it doesn't actually increase the size, it doesn't actually increase the extent, so it runs out of space. So that may be unexpected. So the way we might address that is by changing the extents. One way to change them is using this enlarge node. So if we go to VASA core voxel model, there's a crop node, which we've used before, but enlarge is the opposite of crop. It makes the extents a little bit bigger. So if we connect the voxel model to enlarge and then connect it to expand along Z, and let's enlarge it in the vertical Z direction and the upper Z direction by the same amount that we're enlarging the model. And so now the expand is working as we'd expect. It's maintaining the shape of the roof as we slide this up and down. And if we want, we can view the extents of this expanded voxel model. So, let's, in this case, we have to get the extents from the voxel model because we're not creating it manually. So let's click the extents node. By the way, you can actually get the axes too from a voxel model if you need them. But here again, the extents. Here are the extents of the enlarged voxel model, and if we click extents here, we've got display extents. So now we'll show these extents. So now if we enlarge in the vertical direction, you can see the extents of the enlarged model. And if you want to see those voxels in the corners, we can display corner voxels as well. And so now you got the possible voxel sizes on the corners, just to display them. All right. All right, so now you know about both axes and extents to give you more control over the voxelization process. All right, now let's start talking about visibility. So let's go File, Open. Won't save. Let's load up example 7, direct daylight. Okay, now the rest of the examples in this video are going to focus on these visibility operations and what to do with the results of them, or what you can do. So again, if you go to VASA, we've seen this before, but under VASA operations, visibility operations, there's 4 of them in this version of VASA. The ones I'll be using here are visibility from direction and visibility from point. So visibility from direction you could use for daylight, direct daylight, for example, which is what we're doing here. So here we have here we're looking at 2 voxel models. So the one that's translucent is a model where the filled voxels are meant to represent all the usable space in the building. Basically all the spaces that a person could go to or be in. And the other voxel model is this one yellow, and that's all the voxels that are receiving direct daylight given this certain sun direction. And what this example demonstrates is how to compute a metric from this. So how to compute the number of indoor space voxels that are the percentage of indoor space voxels that are receiving direct daylight. And so here at the bottom we have this metric, which is 4%. So 4% of the space is receiving direct daylight. And just for example, this could be a metric that you might want to optimize. You might want to try to change a design, increase this metric. You may even want to put it into a general design process. And this is not to say that this particular metric is the one you'd want to use, but the purpose of this example, next couple examples, are to give you the ideas of the kinds of metrics you can come up with and how you might implement them. So let's go through how this example works. So what I think I'll do is I'm going to actually hide these so that we can go through everything one step at a time. So first, I'm just going to type display voxels. First, we have our input geometry. So we've seen this before. And now we want to find all the usable indoor areas. So right now this model is hollow inside because they're only voxelizing the walls and solid elements. But what we're going to do is we're going to fill it up. And there's different ways to do this. I mean, if you're using Revit, you may just be able to import the room geometry, and you may also be able to use the door geometry and then fill inside. But here we don't have the doors and we don't have the rooms. So what we're going to do here is we're going to expand all the voxels downwards in the vertical direction. So we've seen this expand along Z node before, but now we're going to expand downwards. And what that's going to do, when we expand down, it's going to fill in all the doors and create this space, which I believe is still hollow on the inside. It's kind of hard to navigate inside. Yeah, it's still hollow, but the ceilings are quite a bit lower. There we go. So, but it's closed. But the key thing is it's closed off. There's no connection from between the inside and the outside, and that allows us to use this fill enclosed regions node. So if we go to operations, fill operations, fill enclosed regions, and we use that node, we'll get the same. It'll look the same on the outside, but the difference is that on the inside, it's completely filled. And now what we'll do is we're going to take that filled model and subtract off all the outside, all the walls, so that we're just left with the inside. And that's what that looks like when we subtracted off all the walls. These voxels represent inside the building. But we're going to do a few operations now to sort of tidy it up. So first, to get rid of some of these small features, we've got these sort of funny features like the insides of columns, for example, are being included there. We want to get rid of those. So what we're going to do is we use this trick where we're going to reduce reduce the size of these filled regions in the horizontal direction. So let's display that, and that eliminates these areas inside the columns and sort of expands the walls a bit and makes these interior spaces smaller. And then we're going to expand it again right after we reduced it. So we're actually reducing and then expanding by the same number of by the same offset. So we're using this offset of 5 to first reduce and then expand. And that just has the effect of getting rid of all those small spaces, like the spaces inside columns. Spaces that humans would not be able to, go into. And then what we're going to do is, because remember that we expanded the walls down in the walls and ceilings down in the vertical direction. So now we're going to expand back upwards, because now our now these indoor spaces are too small because the ceiling has got brought down by too much. So we're going to expand along the Z in the vertical direction, again by the same amount, by the same offset that we previously used to expand downwards. And this is what is giving us the usable space in our building, or at least an approximation of it. Okay, so quite a few steps there. And I should point out that this exact process may not work for every kind of model, but it seems to work for this example. So it requires a bit of creativity sometimes to find the right sequence of operations that get you the result you want. So that's this model here that we had originally. The voxels representing usable inner space. And now let's look at the daylight voxels. So here we're doing our daylight calculation, visible from direction. We've seen this before. So let's actually, okay, we'll just create a display node and go ahead and view that, but it's going to be everywhere because the outside is entirely visible from the sun. It looks a little more interesting from underneath. But now what we're going to do is we're going to intersect this direct daylight model with the other model of the usable indoor space. And so when we intersect the two, there's the intersect node. That's what gives us this. So this is the all the voxels that are visible from that sun direction, but also that are inside the building. And so now we've got these two voxel models, one representing the indoor space, one representing the daylit indoor space, and then we take them and we count the filled voxels in each. So we count the number of filled voxels in the indoor space model using this count filled node, but that's just in VASA core voxel model count filled. So that's saying, okay, there's this many voxels in of indoor space, which is I think 12 million, and then we're taking the model of the daylit indoor space, counting the number of voxels. There's I think that's 500,000 or so, dividing that number, dividing the daylit voxels by the ones that are not daylit, and then that's where we get this number 0.04, 40%. So that's how we can compute that metric. Okay. So that's how that example works. I should point out that we're only doing this computation from one sun direction. It may make more sense. Of course, you may have the sun moves during the day, so it may make more sense to try to have several daylight directions. You could have a vector of a list of daylight directions, and then so you can see the voxels change there as I move the slider. But you could actually feed in several directions and then perhaps average the metrics, average the results across the different directions to get an overall metric. Okay, let's move on. Next, we have example 8, sky visibility. And this example is actually quite similar, although it looks quite different, but it has a number of similarities to the previous one. We're actually using now visibility from point, not from direction. What we're doing in this example is we're computing the I believe it's called the vertical sky components. This is an actual metric that people use, so what that is we're computing the fraction of the sky that is visible from some point just on the outside of the building, like just on the glazing at a certain point. So if we maneuver a little bit, we may be able to get a look at where that point is. There's this yellow line that indicates where that point's located. And if I can get inside this dome, there, inside, we can see that point right there. It's sort of right in the middle of the front of the building, right on the facade there, right where the glazing would be, although we don't include glazing in this example. Okay. And we can see, just like the other example, we've got these two voxel models. So we've got this one voxel model representing, representing the whole sky. We're calling this the sky dome. It's a spherical shell, and then the one representing the fraction of that, which is visible from that point. And then we're counting the number of voxels in each of those models, and then dividing them just like before, and we get this fraction about 29%. So 29% of the sky is visible from that point. All right, so let's go through how we did this calculation. Let's hide those. And where should we start? Let's start with the dome. So what we do there is what we're doing here is we're creating two spheres. And we'll see that this isn't the only way to do it. But we have these two spheres, one's inside the other. They have different radiuses. And I'm going to hide that. And those get voxelized. So we'll create a display voxels node, and we'll take a look at the voxelized spheres. And there they are. And let's actually take a look inside. So I'm going to create a crop node, and we'll crop it in the lower Y direction. We're going to crop off 300 voxels. Let's see if that lets us see inside. It'll take a while to compute that. Okay, and if we zoom in, now we can see we've got two layers. We've got two spheres have been voxelized, and we have this empty space in between. And so we want to give the sphere some thickness. If we create a sphere that has several voxels thick, we'll get more robust results than if we just use, a sphere that's like 1 voxel thick. So we've got the space in between, so we're going to fill it now. And then, the main reason we're doing this, actually, to be honest, is to demonstrate this fill operation. So right now we've got this point, which we can show. And this point, I don't know if you can see that there, but it happens to be right in between those 2 shells. It's that little black dot there. It's hard to see, but it's right in between. So we've got that point. Then we're using this fill from point operation, which is one of VASA's fill operations. And so now, if we view the output of the fill operation, we'll see it does this flood fill from that point, which ends up filling all the voxels in between those 2 spheres. So now we've got a shell of voxels with some thickness to it. And that's what we're viewing. So I'm going to actually delete those nodes that I added, and that's basically, oops, wrong one. That's what we're viewing here. All right. So that's a sky dome. It's a little bit hard to navigate because it is a big model. All right, now let's look at the views from a point. So we had that point. We create the views from that point, and let's actually view that. So I'm going to go display voxels again and view the voxels that are visible from that point. And here they are. And so now what we're going to do is we're going to intersect this voxel model with that dome that had that thickness to it. And when we intersect the two, I'm going to delete that. Here's the intersect node, and that's how we get this model that has the voxels that are both visible and are on that sky dome. All right, that's how, and so that's basically how it works. So that's how it creates those 2 voxel models, which then then the voxels get counted, and then they get divided to get this vertical sky component metric. And of course, this is simplified in that we're only doing the computation for 1 point. You may, one might want to do this for several points on the outside of the building, but this is what we're using in the example. Okay, there's one more thing I want to show you about this example, and that's the extents. So if I'm going to hide that one more time, these analysis models, just so we can see these extents here. And this big box, this big sort of cube-like shape, is what we're using, is the extents we're using for the analysis. Notice that's quite different from the extents of the actual model. We've got this context geometry, and we see that the extents we're using, outlined in black, in the x direction, they're quite a bit smaller than the geometry. In the y direction, they're a little bigger. In the z direction, they're much taller. So how do we get these extents? And the way we used a little trick to do that. So what we did is we created a big cylinder, which we can preview. So just a regular Dynamo cylinder, and we're not actually using this for the analysis. All we're doing with the cylinder is voxelizing it and then creating the extents, and then we don't even use the voxel model after that. So we use the cylinder to create extents, and then we use that set of extents for all of the other voxel models that we use for analysis. So here we're for example, here we got voxel model by geometry and extents to create the sky dome, for example. And for the visibility, again, we're resizing the voxel model using the new extents. So yeah, so that's the trick that we use there. I'm going to turn off that sphere, that cylinder. And one thing that's nice about this trick is it lets us rotate the model, because if we get our extents from a cylinder, it means that our extents will remain large enough even if we do a rotation. So if I find the rotation angle over here, box rotation, let's set that to 45 degrees. It will recalculate the whole thing, that rotation. We'll get a slightly different looking shape because it is an approximation. So the metric will actually change now by a few percentage points. But because we use that cylinder to find the extents are still the right size, and so the calculation still works. All right, I think we're done with that example. Let's open the last one for this video, example number 9, target visibility. This example is similar to the previous one, except instead of asking how much of the sky can we see from a point, the question is how much of some target of interest can we see? And in this case, the target of interest is just this tree, just for demonstration. But you could imagine it could be how much of a waterfront could you see if you're near the water, or how much of a park could you see, or how much of a heritage building, or perhaps there's some landmark inside the building that you want people to see from as many locations as possible. So in this case, how much of some target can you see? And again, we're using this tree in this example, and so what we're doing, and there's many ways of doing this, but what we're doing here is we're projecting the tree onto this imaginary surface behind it. And so we create these voxel models where this one in magenta, it represents how much of the tree can you see from that point projected onto the surface, and then in purple we're saying sort of the how much of the overall tree would be projected to the same surface. And then again, just like in all the other examples, we take the one voxel model, count the number of filled voxels, then divide that by the number of filled voxels in the other voxel model. So the number of filled voxels that you can see projected is 1,856, and then the number of projected tree voxels total, including the ones you can't see, is about 4,500. And so you divide that and you come up with this metric. Okay, so about 40% of the tree is visible from that point. So that's the idea. So again, let's go through how we produce that metric. So what we'll do, let's hide a few things. We'll hide this, and let's hide this. Okay, so we're just seeing the building and the tree. And now let's go through the steps. So well, one thing we have to do is create the surface that we project onto. So let's do that. Let's see what that looks like first. So we're going to create display voxels node. I think I'll give it a color this time, just so it shows up a little better. And give it a color. Just take this color here. And so now let's display that surface. Okay, this is the surface that we're going to project onto. And again, it has some thickness just to make the results a little bit more robust. You know, if you make a surface that's 1 voxel thick, the thickness will actually vary depending on the angle. So it's more accurate if you give it some thickness. So this is very similar to that sky dome that we created in the other example. It's getting chopped off at the top because our extents are not quite so tall in this case. But we actually have a different way, and I think a better way of computing this shell. So this is probably, you know, in the other example, we were trying to demonstrate the fill from point operation, but what we're doing here is actually a better method. So what we're actually doing 2 visibility from point operations. So we're doing visibility from point with no obstacles. So we're ignoring all the obstacles here, just using an empty model, doing a visibility from point within a certain radius. And then we're doing the same thing with a slightly lower radius, and then we're subtracting the smaller filled sphere from the larger one. And so we look at again, if you look at the results of the subtract node, this is what we get. So we get a very nice, it's actually spherical. It doesn't look spherical because we've chopped it off, but it is spherical. We get a sphere. It's actually much more accurate than the one that we got before from actually creating a sphere and voxelizing it. So I would recommend using these visibility from point operations and the subtraction to create a spherical shell if you need one. So that's what that's doing. Then what's next? Well, now we also calculate the unobstructed view to the target and beyond the target. So here we're ignoring all the walls, all the building geometry, but we're including the tree and doing a visibility calculation. And what that's doing is it's giving us the shape that's filled everywhere except just behind the tree. And so now when we take that spherical shell that we just saw, and then we subtract off these voxels, what we end up with is the projection of the entire tree onto that imaginary surface. Okay, so again, quite a few steps, but that's what we end up with. And now, what else do we need to do? We also need to calculate the view from the point, including the building geometry. So let's see what that looks like. And so now we've included the walls, the floors, and everything. And you can see that this column here is sort of severing the view in two, and it's actually obstructing quite a bit of the tree. It's worth just acknowledging that because we're using voxels, we're actually overestimating the size of this column slightly. So we are underestimating the amount of the tree that we can see. This is the amount that we can actually see through all the obstacles. And now if we take that, we do exactly the same thing as before. We subtract this. It's slightly different in this case. We intersect this with that spherical shell. So now we do an intersect, not a subtract. And when we view that, we get, pardon me. So this is one of the more complicated examples. Let me explain that again. We take the views from the point, and now we're not taking the entire spherical shell. We're actually only taking the part of the spherical shell that's behind the tree, and we're taking this and intersecting it with those visible voxels. And that intersection is what gets us the projected area of the tree that we can see from that point. And so this is where we are getting this voxel model. So we have the projected area that we can see, and then we've got the other portion, And when we take the voxel, the projected voxels that we can see, and count the number of filled voxels, and then take the number of the total projected area behind the tree, and count those voxels and divide them, that's what gets us that metric that's telling us that 40% of the tree is visible from that point. Okay, all right. So again, I mean, these are the examples give you some sample metrics, but the main point is not necessarily to use these exact metrics, but rather to be creative and come up with your own metrics, often by doing these analyses using a combination of intersects and subtracts. Then you usually end up counting up the filled voxels and then doing some kind of normalization. This basic technique is the general method for creating metrics using VASA. All right, so please check out the video description for a link to the next video in the series and other resources on VASA. Thanks for watching.